All right. So yesterday, I introduced operations for matrices, starting this matrix algebra, how to put different matrices together to get new matrices. And our ultimate goal is to solve equations involving matrices. So equations of matrices is our goal. And so yesterday I defined for you addition of matrices and scalar multiplication of matrices. And of course, we talked a little bit about what it means for two matrices to be equal. So we talked about all that yesterday. And those definitions pretty much worked out the way we wanted them to add two matrices, for example, we just added the corresponding entries so long as the matrices were the same dimension. Scalar multiplication, I just multiply everything in the matrix by the same number. So those were pretty natural definitions. Today I'm going to talk about multiplying two matrices, and it's just going to be a little more complicated to explain. So let me just nip this in the bud now. Here are two matrices. Yeah, here are two matrices. They're the same dimension and everything. Let's say I wanted to multiply them. It turns out we will be able to multiply these. But what I really don't ever want you guys to do is multiply them the same kind of way that we did with addition, where, basically the way that this is not going to work. So remember, the way this will not work is multiplying corresponding entries. So we're not going to multiply this by just doing 1 times -1 and 2 times -2 and 0 times 3 and 3 times 4. That is bad. What does that give us? That gives us this. Okay, I'm just going to put a big X through this now. Don't do that. So we don't multiply corresponding entries. Unfortunately, or maybe fortunately, depending on your perspective on this, this is more complicated. The actual way matrix multiplication is going to work is more complicated. And there are reasons for that that I probably won't go into. There are mathematical reasons that we want this to be a little more complicated. Unfortunately, they really get into that, I'd have to start teaching you an honest linear algebra course, which I don't want to do. So just take my word for it. There's a good reason that we're not going to do it this way, and I will show you the real way to do it. So purge this idea from your brain. This is not how we're going to multiply matrices. Okay. So let's learn the real way to do it. Okay, so we're going to start small. We're going to build our way up to multiplying matrices. We're going to start with some sort of basic building blocks. And so to do that, I'm going to introduce row vectors and column vectors. So a row vector is a special kind of matrix. These are just special kinds of matrices. This is just a, let's see, I want rows here. A row vector, so I want one row. So this is a 1 by n matrix. So a row vector is just a 1 by n matrix. Remember, when I talked about dimensions, these two numbers represent the number of rows and the number of columns. So if you're a row vector, you just have one row. It's just a single row, and then I have however many columns I want. So that's what a row vector is. I'll use that term a lot. And for example, I don't know, here's a row vector. It's a matrix with one row and it has 5 columns. So just 5 numbers in a row. That's one. And then the vertical version of this is a column vector. And this is just the opposite. This is a m by 1 matrix. So now instead of having a single row, I have a single column and then however many rows I want. So here's another example. A column vector, 1, 2, 3, 4. Just a single column. In this case, I have 4 rows. This would be a column vector. Okay. So to make this all work out, I'll get my cat out of here. To make this work, what we're going to do is learn first how to multiply a row vector times a column vector, because this will sort of be the easiest case. It's multiplying 2 of these together. And then we're going to see how we can use that to describe multiplying 2 matrices. So let's learn how to multiply a row vector and a column vector together to get a new matrix. All right, so multiplying row times column. This will be our first goal. So we have to just be a little careful. So just like how addition was not always defined for two matrices, if the dimensions weren't the same for addition, I couldn't multiply them. There are going to be sort of dimension restrictions for multiplying as well. So if I want to multiply a row vector and a column vector, I have to make sure one thing is true. So here's what we're going to do. So we're going to suppose I have maybe, we'll call it C for, well, actually, how about we do R first? We'll have R is a row vector. So maybe it has R, I don't know, IJ, or yeah, I guess I'll go ahead and use that abstract notation. Again, I'll use the abstract notation that I introduced yesterday, but then I'll give you some examples that maybe try to flesh this out a little. Yeah. So here's a row vector, and let's say it's a 1 by, I don't know, n row vector. And then we're going to have a column vector C as a column vector. And I want the dimension of that column vector is a m by 1 column vector. So we'll just start with these assumptions. I just have a row vector and a column vector. Then to multiply them, which I'll put R times C, row vector times column vector, is the following matrix. This is a matrix where, I don't know what that noise was. Anyway, this is a matrix where the entries are the following. And trying to think how I want to write this. I'm probably going to making this more confusing than just showing you some examples and explaining. Here's what I want to do. I want to do R, let's see. Yeah, okay. I don't want to use a certain notation for you guys. This will work. So this is probably going to look really abstract and confusing. And so pretty much what I'm going to end up having to do is just give you guys an example. All right. So these are my entries. And the idea is that I'm sort of multiplying corresponding entries of the row and the columns, but I'm going to add a bunch of them up. And so this is sort of abstract notation for this. Let me just give you an example that more or less illustrates what I just wrote on the board, but maybe in a more intelligible fashion. So let me write this on the board as an example. Multiplying a row vector and a column vector. And then we can talk about dimension and all that stuff. All right. Let's just see an illustrative example. How about R is this row vector? How about we just do 1, 2, 0, -1. So it's a 1 by 4, and then we'll have C as my column vector is like this. 2, -3, 0, 1. Okay. So I have these I have this row vector and I have this column vector. I'm going to show you how to multiply them. This will be, we can do more examples of this to flesh this out some more. To do this, that abstract formula that I wrote on there, what it really meant was take the first entry of this guy and the first entry of this guy and multiply them. Take the second entry and the second entry and multiply them. Take the third and the third and multiply. The fourth and the fourth and multiply. And then add all of them together. Add all of them together. That's what we want to do. And so we're going to do that. And it should be a matrix, but it's going to be, in this case, it'll be a 1 by 1 matrix. It's kind of weird. But let's figure out what that means. So we'll do 1 times 2 is 2. 2 times -3 is -6, so 2 minus 6. 0 times 0 is 0. And 1 times -1 is -1. And it's a 1 by 1 matrix, so that means it's just a number inside of brackets. It's kind of silly to have a 1 by 1 matrix, but that's what the result is here. So what is this number? Well, let's see, 2 minus 6 minus 1, that is 2 minus 7, that is negative 5. Okay. And since a 1 by 1 matrix is kind of just a number inside of brackets, we're going to be kind of sloppy and just call it a number, right? So just kind of forget about the brackets. So if you wish, when I multiply a row and a column vector, I get a number out of it. Yeah, we'll just agree that I get a number. So when I take a row times a column, I get a number. But so to walk back through how that worked, all we did to multiply a row vector by a column vector was take the corresponding entries, so first times first, second times second, third times third, and fourth times fourth, and then add up all of those results. That's how that works. And in this case, we get negative 5. Okay, let's see another example. And then we'll, one more example of this, and then I'll show you why the dimensions need to work out. Another example, how about r times, r equals 0, negative 3, 4, 5, 1, negative 1, and c equals 0, 0, 0, 1, negative 1, and how about 7? Why not? Here are two vectors. I have a row vector and a column vector. We're going to multiply these two together, just like the last example. Again, all this says is take the first thing from the row multiplied by the first thing from the column, second times second, third times third, and so forth, and then just add up all of the results. And we're just going to treat it as a number, so I won't even write the brackets this time. We'll just get a number out of this. So 0 times 0 is 0. Negative 3 times 0 is 0. 4 times 0 is also 0. 5 times 1 is 5. 1 times negative 1 is negative 1. And negative 1 times 7 is negative 7. And so we simplify this, and what do we get? Well, zeros don't contribute anything. 5 minus 1 is 4, and then minus 7 is negative 3. So r times c is negative 3. These two. Okay. Okay, so this is sort of how we're multiplying the row and the columns work. You might go back and look at that abstract definition I wrote, maybe try to make sense of it. All I'm doing is trying to find a way to say, pair up the corresponding entries and multiply them and then add up the results. There's certain notation that maybe you guys don't know that I don't really want to introduce that would make that easier to describe. So that's why I kind of struggled there for a second. But we'll leave it at this. Maybe these examples sort of make clear what I'm trying to get at. I don't know. If you guys have any questions, maybe I should pause and ask. Do you have any questions? Okay. So this is row times column vectors. And we should notice that the dimensions have to sort of work out. So if r is a row vector, which is a 1 by m row vector, and if c is a, I guess it doesn't matter, n by 1 column vector, then the only way that this is going to make any sense, the only way that I can define, this multiplication is if the dimensions match up. And when I say match up, what I mean is m and n better be the same number. i.e., this row vector and this column vector better have the same number of entries in them. Because as you notice, part of our multiplication was pairing up the entries. And so if they don't have the same number of entries, I'm going to have things that I can't pair up. And so it won't make any sense. So it'll actually be undefined. So if m is not the same as n, RC is undefined. So you have several exercises on your activity about when matrix multiplication is defined or undefined. So it's good to start thinking about when they're undefined.